Hello and welcome to lecture 47. We are discussing recent advances in turbofan engines. So in last lecture we were discussing about Rolls-Royce ongoing project on ultrafan and advanced concept. We also have discussed about the NASA project about say high tech, and then we were discussing about the propulsive fuselage concept and turbo electric propulsion system. So if we look at all what we have discussed up till now, that's what is mainly been focusing on commercial engines. We will say what about say military engines, because we know these military engines are also coming under category of turbofan engines. So let's try to understand the military aero engines. So before starting, let's look at this plot. That's what is giving the different kind of information. It says on x-axis we are having say turbine entry temperature or inlet temperature and thrust to weight ratio. When we are talking about say application for military as well as for commercial aircraft, our expectation is more towards say thrust to weight ratio, but here this thrust to weight ratio is different compared to our commercial engines. So let's try to look at. So this is the third generation engine. We can say it is R29B 300, where the turbine entry temperature, that's what is in the range of 1400 Kelvin, and roughly thrust to weight ratio is around 6 to 7. And if we look at carefully the bypass ratio for such third generation engine, it was around 0.7 to 1. Fan pressure ratio is approximately 2.5. Overall pressure ratio is slightly on the lower side, say 13 to 20. Turbine blade material, those days it was equi-axed. Propelling nozzle, mainly it's a conversion nozzle, and control systems, they are hydraulic and pneumatic system. So this is what is called third generation aero engine. So let's move towards the next. So here this is Eurojet 200, that is defined as a fourth generation aircraft, where the bypass ratio, that's what has reduced from say 0.7 to say 0.2 to 0.6. Fan pressure ratio also is raised, overall pressure ratio also increased. At the same time, the turbine entry temperature, if we look at, it is on the higher side, and that's the reason why turbine blade material also is changed. The nozzle is more conversion diversion, and at the same time control system, that also has changed to full authority digital engine control. So we can say over the year the advancements, that's what is going on in say military engines, and that's what we are defining in terms of generation of aircraft. Here the thrust to weight ratio is in the range of say maybe 8 or 8.5. Next we have, it is our fifth generation aircraft, say recent engine F135, or say we have our fighter 35, that's what is coming under this category, where the bypass ratio further it has been reduced to say 0.3 to 0.5. Fan pressure ratio is moving on the higher side, it is more than 4.5. Overall pressure ratio is also higher. At the same time the material is single crystal blade, and this propelling nozzle, they are with the thrust vectoring and integrated engine and flight control, that's what is a control system. Basically what all we are discussing, that's what is deciding the generation of the aircraft. Here in this case thrust to weight ratio is say roughly in the range of say 10. Say next, when we are moving, it is called sixth generation aircraft, or we can say it's a future engine, where the turbine entry temperature will be more than 2200 and expected thrust to weight ratio, it is in the range of 14 to 15. And here we can say the bypass ratio, it is not fixed, it says it's variable. Fan pressure ratio is on higher side in the range of 5.5. Overall pressure ratio is 35 to 45. The turbine blade material, with the advancement of technology, it is ceramic matrix composite, and Here this propelling nozzle if will be say FTV, and control system it is intelligent control system. So let's look at how we need to understand this military engine. So this is representing the generation from third generation, fourth generation, say 4.5 generation also is coming in between. Then we have fifth generation and the future engine, that's what is thrust generation. So it says over the generation, that's what is turbine entry temperature is going higher and higher. At the same time, thrust to weight ratio expectation also is going higher. So let's look at one of that engine. This is the fifth generation engine, that's F135, which was designed and developed by Pratt and Whitney. Here in this case, if we look at, they have two configuration. There are number of configuration which are being explored by Pratt and Whitney. Say it is conventional, say takeoff and landing. Here in this case, if we look at, we are having fan that will be followed by bypass duct, and here we are having say HP compressor, HP turbine, and we are having say LP turbine that will be followed by the afterburner. And here in this case we have special kind of say conversion diversion nozzle. This conversion diversion nozzle, that's what is been used for the specific purpose here. That's what we say in terms of vertical takeoff. So let's try to understand the other configuration. This other configuration, it is say configuration of PW600, where we have a fan combination, that's what is being placed in the front. So if we look at here, this is representing the overall picture, where as we have discussed, this nozzle it is with 3 bearing swell duct. So that's what will be rotating as per the requirement, and the exit area can be vary as per the requirement in terms of say petals. So those who have not attended the second week classes, just go through that, where we have discussed about the construction of nozzle, and there also we have explored some of the possibility in terms of variable area nozzle. Here there is a shaft which has been connected with this fan configuration. This fan, it is counter rotating configuration, that's what will be helping in terms of generation of the lift. So we can say by swelling this nozzle downside, that's what will be giving the vertical takeoff, and in order to counter or in order to balance, there is a lift fan which has been provided in the front, and this fan it is been designed by Rolls-Royce. Here there is a special arrangement of say roll nozzles which will be taking care when we are having say vertical takeoff, it will be balancing the rolling moment on both the side. So if you want to look at how exactly it is working, this is the site, YouTube video is available. You can go through in order to understand how this engine is working. And as I told, this is what has been fitted with say F-35 engine, say aircraft. So let's look at what all are the advantages in terms of F-135. Here, this technology is a proprietary technology. We can say it's a confidential project, or at the same time we can say it is coming under say export control. So limited information, that's what is available for this engine. So what all is available in open literature, based on that we have tried to put the advantages of F-135. There is nothing to discuss in terms of commercial aspect. Let me clarify here. So here in this case it says it is been designed with the stealth features, and that's what will be saving, or it is giving the say detection, or say it is reducing the IR signature, and that's what will be used in order to have the detection risk, and that's the reason why it is of more popularity. Second, that's what is in terms of versatility. As we have discussed, this engine it is been made for different applications. So F-35 they are having different variants. So it need to perform various missions which are maybe air to air combat or air to ground strike, intelligent gathering or reconnaissance purpose. So all these purposes, so it's a versatile kind of engine. At the same time, it is having high thrust to weight ratio as we have discussed, and that's what is giving the agility, acceleration, and overall performance under different flight regimes, including supersonic speed also. And fuel efficiency, it is one of the major attraction. That's the reason why it is extended with the range and the endurance limit for the mission. Here, since it is working under very high temperature configuration, that's what is required, a special kind of say attention in terms of cooling. That is what has been taken care of in F135 engine. Say since the operating temperature is higher, overall pressure ratio is higher, and there we are looking for the special kind of material. We are looking for say lightweight composite or heat resistance alloy. That's what is being used in order to reduce the weight and to improve the overall performance of the engine. And this aircraft engine can attain very say supersonic speed very quickly, and that's what is giving the attention in terms of say achieving the supersonic speed at very short duration. So these all are the listed advantages in their web page and in open discussion. So let's try to understand what all are the challenges for this engine. So very first challenge we can say, since it's a new kind of engine and it is high performance military engine, that means it is very expensive in terms of design, development, production and maintain. And that's the reason why when we say the countries, those who are having this F-35 aircraft, they are the richer countries. So you can understand what we mean by the cost of this aircraft. Next, it is in terms of weight. We can say the overall weight, it is slightly on the higher side because of the complexity in terms of design and use of material. The maintenance, since this technology it is of different kind, and that's the reason why it is subjected to higher maintenance cost and logistic challenges also. At the same time, it need to be used at different environmental aspects also. So in terms of development time, since this is what is a cutting edge technology, it took a lot of time in terms of research, development, testing, certification, and all those. That's what is required at time. And the delay in supply of this, that's what will be impact on say the sales of these engines. At the same time, the supply chain, that also is important, since this is coming under say export control, and that's the reason why it is very challenging to have this kind of engine. Same way, operational consideration, when we are using that, that's what is required, a special kind of operations, so special kind of operating characteristics are required, where it is more challenging to use this kind of engine. And since it is operating as high temperature, that required say very good thermal management system, because it will subject it to have very high heating, and that's what will be deteriorating the performance of the engine, or maybe in terms of failure of the engine. So we can say this is a new engine, what we have discussed in terms of 5th generation aircraft, and many countries they have opted with this aircraft, and that's what is under sale, under development for the different mission requirements. Let's try to understand this different criteria here. So what all we have discussed, we have say 2-spool turbojet engine, we have suppose say 2-spool turbofan engine. Let's try to look at what all we have discussed up till now in terms of our understanding. What we mean, for say turbojet engine, we are having say higher exit velocity, and that's what will lead to increase the thrust developed by this engine. So if we look at turbojet engines, they are having very high thrust generation capacity with say higher exit velocity. And if we look at, this is simple in terms of design, and they are more efficient, we have discussed in terms of achieving the supersonic speed. So these are the benefits of 2-spool turbojet engine, what all we have explored during our week 3 and week 4. Let's look at in terms of what all are the challenges. Say what we say, we are looking for the efficiency. We have constraints in terms of say temperature, and that's where the challenge is coming in terms of improvement of efficiency, specific fuel consumption, IR signature as well as noise. So these are the challenges for say turbojet engine, and that's the reason why people they move towards say turbofan engine kind of configuration. So let's look at what are the benefits for say two-spool turbofan engine. They are with the improvement in terms of efficiency, lower specific fuel consumption. We have say jet noise suppression. At the same time, it is less susceptible for say infrared detection. So what all are the limitations we were discussing for turbojet engine? That's what will be overcome by incorporating this turbofan engine. So let's try to understand, can we think of say engine where we will be having the benefit of both turbojet as well as turbofan. So that's what will be fulfilling our requirement for say subsonic requirement and supersonic requirement. Suppose if we are discussing for the military application, we can say supersonic mission, that's what is a major requirement for the military engine. At the same time, when we say subsonic operation, that's what we say the benefit in terms of say specific fuel consumption. So let's target the advantage of these two engines. What are the advantages we need to take up with? It says for turbojet engine, that's what is giving higher specific thrust. At the same time, this turbofan engine, that's what is giving the benefit in terms of lower specific fuel consumption and lower emission. So we are now moving towards the development of new kind of engine where we will try to enhance the performance of the engine, the same engine that can work under two different categories. As of our requirement, it will be work as a turbojet engine. As and when required, I can use that as a turbofan engine. Oh, is it possible? Let's try to look at, because what are our requirement? As we say, we are looking for the benefits of both. So what we have understood, it says when my engine it is working under off design condition. So when we say off design condition, we will be having say our cycle parameter, that's what will be changing. Sometimes we need to have compromise in terms of power as well as poor component performance. So as and when we are looking for a special kind of configuration where we want to remove the limitations in terms of poor performance. Is it possible with? So let's try to look at, if we are looking for the special kind of configuration, we want to operate our aircraft both in subsonic and supersonic flight condition. So we will be moving with the active control of the cycle parameters, which can be achieved as per the requirement. So we will say, what is this? Okay, is it possible to control the cycle parameters? The answer is yes. That's what is called variable cycle engine. It is nothing but it can optimize the cycle parameter in order to meet a special overall performance. That's what is required for the specific flight conditions. Now remember one thing, the cycle, what we mean in our thermodynamics is the completion, or maybe we can say from one end it will be starting and ending at the other point. Here the variable cycle, it is in terms of operation. So do not get confused with the terminology of cycle. So let's try to look at what is the meaning of that. So here if we look at, this is representing say the engine, and speciality of this engine, here you can say it's written say VB1, it's VB2, here somewhere it is written VB3. What is VB1? It is say, if we look at, it says variable say injector or say it's a selector valve. That's what is being placed at the end of the fan. So here if you look at here, this is a kind of switch, or we can say we can open and close this valve. We can say this as a valve. Okay. Same way here in this case it says VB2, it's a valve. That's what is used to open and say close as per the requirement. That's what is being placed here. It is called say core driven fan. So this, if we look at, it says a two spool kind of configuration where the LP turbine which is used to rotate this fan, and this HP turbine, that's what is used to rotate HP compressor as well as this fan. Okay, we are having VB3, that's what is say variable area bypass nozzle. That's what is used for the mixing of our bypass duct and the core here in some region. And here if we look at, it says we have afterburner, and at the exit we are having variable area nozzle. So it's a different kind of configuration we can say. So it says it's a mixed kind of configuration which can be used for all our flight conditions, subsonic condition, transonic condition or the supersonic condition. And here in this case our major requirement is in terms of say fuel economy both during supersonic and subsonic cruise as well as noise. Now the question will come, why are we thinking about the fuel economy? Up till now what all I was discussing, we used to say for military engine we are not bothering of fuel economy. But now the time has come. Suppose say if we want to have the continuous flight from one location to other location without any stoppage, where we will not be requesting someone to have landing and then refueling and all those aspects. Under that configuration, we are looking for the fuel economy during the cruise operation. So basically we want to increase our range, we want to increase our endurance. At the same time, we also need to focus on the noise. Okay, so let's try to look at, this is representing the working of this variable cycle engine. Here in this case, if we look at carefully, it says we are having VB1 that's closed, VB2 also is closed. So here if we look at carefully, there is no bypass, that's what is happening from this fan. There is no bypass, that's what is happening from this other fan. So we can say this engine is working similar to our turbojet engine. Okay, so the thing is, when we will be using our turbojet engine, what is the requirement? When our thrust requirement is higher, under that configuration, or say when we are looking for supersonic speed, we will be running our engine as turbojet engine. Let's look at here. Suppose if we consider my VB1 it is open and VB2 that's what is closed. So under this configuration, this engine is working like turbofan engine. Yes, just look at here, this is my core engine and here I am having bypass duct. Similarly here if we configure, in this case suppose if we consider, say we are having VB1 and VB2, they both are open. Okay, so both the valves are in open configuration where we will be thinking in terms of operation as conventional engine. Okay, suppose if we consider here in this case, I will be closing my VB1 and I will be opening my VB2. So that's what is acting like a bypass kind of configuration. Now this all we are discussing, it seems easy to discuss at this moment, but let's try to understand what is the meaning of that. What basically are we looking for is we want to have this engine, that's what will be working under different configuration as per my requirement. That means in terms of turbojet engine as well as turbofan engine. Okay. Now let's see what all are my requirement. I say takeoff, where the major focus it is in terms of thrust requirement, and if you look at, we are looking for our exit velocity to be in the range of 400 meter per second. We are focusing on noise level, so we want to suppress the noise. At the same time, what is our requirement? We say we are looking for, say, higher amount of thrust. Okay, suppose if we consider we are looking for, say, subsonic operation, so most of the time we are operating our aircraft under subsonic condition, or we are running our engine under subsonic cruise condition, where we will be considering more in terms of fuel economy, or we want to reduce the fuel consumption. So under that configuration, the engine size, that's what is influenced the nacelle drag. So we need to have a kind of configuration where we will be focusing in terms of fuel economy. So we can say our turbofan engine, that's what is acting fine under this configuration. Similarly, as per our requirement for the flight envelope, we are looking for supersonic cruise. Under that configuration, my engine, say, size, that's what will subjected to shock wave, and that will be increasing, say, drag. So now we need to move with, say, design of the engine, that's what will be fulfilling all these requirements. Okay, so what all are the possibilities? We have, say, variable cycle engine. At the same time, we need to move with, say, variable geometry kind of configuration. What are the criteria? We say we are having, say, supersonic point, subsonic point, say we have takeoff configuration. So we need to go with, say, design optimization for takeoff configuration, supersonic and subsonic configuration. We need to go with the component matching and all those aspects. Now let's come to the point here. Let's look at this engine carefully. Suppose if I say I am operating this engine as turbojet engine. So we can say, as per the requirement, the mass flow rate, that's what is flowing through my compressor as well as combustion chamber and our turbine. Okay, now suppose, say, if I will be putting one of the valve open, under that configuration, the mass flow rate which is going into core engine, that's what will be reducing. So that will not be generating the sufficient amount of power in order to rotate the compressor. So in order to have same power to be generated to run this compressor, we need to increase the velocity at, say, the entry of the turbine. It is called variable area nozzle vane. So by changing the area between, say, nozzle vane, we are able to increase the velocity of the exhaust gas, and that's what will be striking on the rotor of the turbine, and which will be generating same power as per the requirement. So it is very complex in terms of understanding. So maybe when you go ahead, when you go or read in detail, you will try to realize the complexity of this kind of configuration. So it is not only that we will be putting the valve here and that's what will serve the purpose. We will be having, say, variable kind of vanes we need to incorporate both for compressor as well as for the turbine. Okay, so let's move towards the configuration. This is the configuration, that's what has been proposed by Pratt and Whitney. So here in this case, if we look at, we are having the bypass stream here, and this is our core engine. So during takeoff operation, if we look at carefully, what will happen? We will be having, say, this noise what is being generated by this jet that need to be suppressed. So under that configuration, we will be having the opening of this particular stream. So that's what will be giving the inverted kind of velocity profile. Okay, so under takeoff condition, we will be taking care of noise suppression. Suppose, say, we are looking for supersonic cruise where my thrust requirement is higher. So in bypass duct, if we look at, there is a kind of combustor, it has been placed in this combustor, that's what will be burning the fuel, and that's what will be generating the flat velocity profile. So it's a variable stream kind of configuration where we will be achieving, say, supersonic cruise. So burner, that's what is on even in bypass stream. Say when we are operating under supersonic cruise condition, there we will be putting our burner in off condition. So majority of the thrust, that's what will be generated by our turbojet engine. So this kind of configuration, there are number of configuration which are being explored by number of companies, number of researchers from different universities. So the configuration what all we are discussing in terms of variable cycle engine, it is not a new concept. People, they started exploring this kind of configuration during 70s. So you can say it's almost 50 years back people, they have explored the possibilities. Now with the advancement of technology, with the advancement of computational facility, experimental facility, people, they realize that this also can be explored as a future engine requirement. Okay. So this is a configuration which was been explored by GE, what all we have discussed in terms of VB1, VB2 and VB3. This configuration, it is for XF, YF, F120 variable cycle engine. So GE also is working on the development of this variable cycle engine. So let's look at what all are the ongoing projects in this configuration. So the project, it is called, say, ADVENT. It is Adaptive Versatile Engine Technology. There is a project, it is called Versatile Affordable Advanced Turbine Engine. Under that category, different ongoing research we have. It says the requirement, it is to improve the specific fuel consumption by 30%. And in order to meet this requirement, there is a requirement for, say, overall compression system, variable cycle technology, advanced high temperature material technology. That's what is required to meet, say, power as well as, say, the energy, thermal energy. So these are the engines which are under development in US. Even these engines are under development by different countries. When we are discussing about the military engine, it's a proprietary nature kind of work, so no details, that's what is available in straight way. But let's try to understand what understanding we have. So here in this case, one of the requirement, as we have discussed, it is IR signature. These IR signatures will be mainly from your turbine section and the exhaust of the nozzle. So innovative kind of nozzles, they are being designed so that will be suppressing the IR signature. At the same time here, a specialized stream, it is been provided, that's what is acting like a cooling barrier, and that is suppressing the nozzle, say, IR signature. Let's look at, this is a variable cycle engine. So more detail you can go through the web page by GE, that is Adaptive Versatile Engine Technology. Here in this case, what all we have discussed, in line to that we have this configuration, and in order to suppress the IR signature, this nozzle, it is been specifically designed. Now in terms of understanding this ADVENT engine, this is representing the snapshots. So here if we look at, this is acting like a conventional turbojet engine. We have bypass kind of configuration, and here we are having combustor. So that's what will be acting like a supersonic cruise condition. At the same time, here as we have discussed, there is a specialized line which has been provided to act like a cooling media. Okay. Now there is another development which is going on with a special application for UAVs, transport aircraft as well as for ISR. So the approach, it is to combine the next generation ultra efficient engines with the target of 35% improvement of fuel economy. At the same time, reduce the emission and noise and increase the power extraction. So here if we look at carefully, this is more in terms of stealth technology. So here we have engine and this is representing the intake. So basically IR signature, they are being captured mainly at the entry or inlet, secondly at the exit from the nozzle, and third, that's what is from this turbine section. So a lot of research it is going on in proprietary nature. So that's what is exploring the possibility of such engines to be applied for UAVs, transport and IRs. Now let's look at what all are the advantages. So here, as we have discussed, we are focusing this engine because we are more interested in better fuel economy under different flight conditions, and we have the optimization in terms of compression ratio and bypass ratio. That's what is helping us in terms of reducing the specific fuel consumption and improvement of the efficiency. This is enhancing the performance in terms of our different operation requirements like takeoff, climb, cruise, supersonic flight. Even that's what is increasing the agility, acceleration and speed. At the same time, this is increasing, say, the range of the aircraft, and that will give, say, the global operation say opportunities. And it is more versatile kind of engine. That's what is of need since long. This engine can also be opted for commercial aircraft, and we are able to achieve, say, higher supersonic efficiency, say reduce environmental impact, the noise reduction during different operation. That's what is a major advantage, and this has main application as of now. People, they have explored in terms of military applications, and it has different innovative technologies in terms of new upcoming materials, design and control systems. But at the same time, what all we are discussing, that has lot of challenges. So if we look at it, seems simple in terms of operation and understanding, but it is more complex, and that's what is required special kind of attention in terms of adjustment of component, control system design, manufacturing, maintenance. So it is more complex. The weight, because of additional components, it's a bulkier one. So when we are talking in terms of payload carrying capacity, that may reduce. The size of this engine is higher because it has special kind of control mechanism, control devices like variable stator, variable exhaust, all those things. That's what will be increasing the size. At the same time, because of the incorporation of these devices, it is a question mark in terms of reliability of this engine. At the same time, here, since our operating temperature is higher and it is operating under different modes and different condition, that's what is putting more challenging in terms of, say, thermal management. Control system, that's what is a sophisticated control system. It is required. It need to be used for various phases. Certification and regulation, it required extensive testing, certification and approval from the regulatory body. At the same time, for the development of such engines, it required a lot of time because it required a lot of research, testing, and to make it commercial readiness, it is a huge investment itself in that sense. And you can imagine many countries separately, individually, combinedly, they started exploring such kind of engine development activities these days. The maintenance and support, we can understand, say, since it's a military aircraft, so we have the cells of this is to selected countries, and when it is coming in terms of, say, maintenance, support, all those things, that's what is required, lot of investment. At the same time, the training to this maintenance personnel also is a question mark. Okay, convincing this aircraft manufacturer and operator to opt for this technology, it is, people, they will more focus in terms of cost effectiveness as well as long term reliability. And the technological maturity, that is still is a question mark in terms of risk assessment and reliability for the application for different models. So when we discuss about the military engines, it is always very challenging in terms of all aspects, starting from design, selection of parameters, then material what we are using, operating, as well as fixing or fitting of this engine. All these are more challenging in sense, and that's what is required. Lot of understanding, lot of maturity, lot of experience, and to have the share of knowledge between different experts, different countries. And that's the reason why the major bread and butter for the engine manufacturing companies is more in terms of military engines. And that's the reason why for many countries it is always coming under export control, and they will not disclose the technology. So here we are stopping with this discussion on the military engines. I'm sure what all we have discussed in terms of military engine, you have more excitement, but because of limited time and limited information available in open source, that's the reason we will not be exploring more in this discussion. Now in next lecture we will try to discuss a new kind of configuration. That's what will be used by say airline companies, both say commercial as well as military, and that's a special kind of configuration. So it's a surprise to you. Let's see you in the next lecture. We will be having more discussion on turbofan engines. Thank you very much.